Welcome to my screen lesson on reaction mechanisms for you chemists. All right, so a reaction mechanism is basically a series of elementary steps or smaller steps that make up an overall reaction. So as we can see from my first example, there are two what we call elementary steps to the entire reaction, and there's not usually any more than two reactants in an elementary step, because that is reasonable that two different molecules could collide with each other as opposed to three or four. Another thing about reaction mechanisms is that all of the elementary steps have to add up to be the overall reaction. And that can happen in more than one way. So when we look at a proposed reaction mechanism, that is one possible correct answer to how a reaction is really proceeding behind the scenes, but there could be other possibilities. Because we can't really see it, we really aren't sure, but we do know that it has to abide by certain rules. There is always a slower step. So if you have 2 steps, 3 steps, even 4 steps in a reaction mechanism, one step will be called the rate determining step or the slow step. And it's like, for instance, making toast in the morning, you have to get the bread out of the bag, maybe the margarine out of the fridge. That's pretty quick. Then you put the bread into the toaster. That takes a long time. Then you butter the bread or the toast, and that's quick. So the whole process is held up or determined by the toaster. That is your rate determining step, and all reactions have a rate determining step as well. All right, so when we look at the different elementary steps, we can identify reaction intermediates, which you have defined as being short-lived products that are made and then immediately used up again. So if we look here, this I2O is made in the first step, but then in the second step, it gets gobbled up. So that means it gets canceled, and that is a reaction intermediate. Okay. Now, the other product that's made here is water, and it is not consumed in the second step. So that is our only reaction intermediate in this particular reaction. Okay. Now, a catalyst, as you have studied already, is something that is added to a reaction, and it makes it go faster. And really what a catalyst does is it changes the mechanism. So with a catalyst compared to without a catalyst, you're going to have entirely different products, intermediate products during the reaction, and that can change the amount of energy and therefore the time the reaction takes. So a catalyst needs to be present as a reactant at first, and then later it's still there at the very end as a product. Okay, so if you look here, you'll see solid iodine was added as a reactant, but then later at the very end, there it is again, identical. And that is very characteristic of a catalyst because they are not used up or consumed during a reaction. But their presence basically makes the reaction intermediates require less activation energy. Therefore, more collisions are successful or effective, and the reaction ends up going faster by it being present. This reaction, just by the way, is hydrogen peroxide being broke down, and you've all, I'm sure, witnessed this demo or seen a video. Sometimes we call it elephant toothpaste, very, very foamy, and adding iodine definitely makes it happen much faster. It would break down on its own, but at a much slower rate. Okay, so once we have identified intermediates and catalysts and canceled them out because of the fact that they're on opposing product reactant sides, whatever is left is the overall reaction. So we've got our H2O2, and then if you look on all of the reactant side here, there is actually a total of 2 of those. Okay, so rather than putting H2O2 plus H2O2, we should just put those together and say that there are 2. And it is going to decompose into anything on the reactant side. So once again, you can see that there are 2 liquid waters. And then there's an oxygen gas, which is why it's always so foamy. So there's our overall reaction. Now the rate law equation, there's a relationship basically between the slow step or the rate determining step and the rate law equation. It only works for the slow step, but basically in the slow step, I'm just going to put a little note here, or the rate determining step, we have, some number of reactants probably reacting with some number of other type of reactants, and we are making products. So that M and N you might recognize from our rate law equation lesson previously, that is the exponents that we raise the product concentrations to. So with the slow step only, the concentration of reactant X will be raised to its coefficient. Likewise with Y, raised to its coefficient. Okay, so if we look up here at the slow step, we see H2O2, of which there is an imaginary 1 in front, which means it would be raised to the exponent 1. So K times H2O2 raised to the exponent 1. And that 1 is coming from here. Now, you might wonder why we're not including the iodine. Anything that has been crossed out, do not include. Okay. So that could be catalysts or reaction intermediates. I'm just going to call those Ri. Okay, so if you've crossed it out, it's not part of the rate law. All right, so for a second example with just a few variations here we have another mechanism. This time I haven't told you which step is slow and which one is fast, but I have given you the final rate law equation, which is going to allow us to figure that out. So first of all, we're going to do the overall reaction again. So we're going to look for things to cross out. So here we have produced a single fluorine atom, and in the second elementary step, we use it up. So that is going to cancel, and fluorine is a reaction intermediate. Now we're looking for catalysts. Catalysts would have been on the reactant side and then still present when we're done. So in this particular reaction mechanism, there are none. No catalysts at all. And there doesn't have to be a catalyst. It's great if there can be, but there doesn't have to be catalysts in all reactions. So now our overall reaction is going to be, it looks like if we add up, we've got 2 NO2s on the product side and a fluorine. And we are going to end up making 2 NO2F. Okay. Now, part C is wondering which step determine which elementary step is fast and slow and write in the brackets provided. So what you want to do here is look at the rate law and realize that, those are raised to imaginary 1s, and find a step that you could have a corresponding 1 in front of those, which is clearly step 1. So this is the slow step, this is the fast. By the way, it's just ironic that both examples I have on this sheet have the first step as the slow step. That does not have to be the case. Okay. All right, now we are going to draw a little graph of this reaction. So a bit of review. Endothermic reactions are reactions that consume heat from their surroundings and therefore end up feeling much colder. And when they're finished, their kinetic energy is low and therefore potential energy must be high. So if we, just start at some imaginary number, we're just doing a sketch. This is not quantitative in any way. We definitely have to end up being higher in potential energy if it's going to be an endothermic reaction. With exothermic, you'd have low potential energy after because you'd have high kinetic energy, and that's why the temperature would feel so much warmer after an exothermic reaction. So we know that. Now, in terms of this reaction, we have two elementary steps, and we have now seen examples where that tells us there is going to be two bumps on our graph. Okay. Now, the question is which bump should be higher and which one should be lower? Well, the slow step takes more activation energy to overcome. So that is telling us that we are going to have a big bump and then a smaller bump and then taper off. And I'm just going to erase this now. I'm still higher. My graph didn't allow me to go quite as high as my original dot there. And again, this is just a sketch. Okay, so this is the slow step. And this is our fast step. And there is less activation energy needed for a fast step. And that's why your little bump on the graph should be less, not as high. Okay. All right, so the overall enthalpy change would be, in a quantity between here and here if we had numbers on our graph. And the second part of this question asks us to now re-sketch this if we were to use a catalyst. And a catalyst would allow an entirely different mechanism with elementary steps to take place, but it's going to be able to go faster because it is not going to require as high of activation energy. So with a dotted line, again, this is just a sketch, you're just not going to have to go as high. Okay, but your overall ending and beginning of energy, like your enthalpy change, wouldn't be any different. But to get the reaction to happen, you would not need quite as much. I should make that just a little more obviously higher than our second one, though. Okay, and that is it. And hopefully that is helpful for your assignment that you're going to be doing. Thank you. Bye-bye.